detecting and parking in front of a colored cone. This lab deals with robotic vision, and in specific visual servoing. Visual servoing is important in autonomous vehicles as it allows the robot to act based on the information gained from its external environment. These decisions are made after combining computer vision and pattern recognition on data received from the sensors on the robot, in this case, a Z stereo camera. Having this capability will help the robot traverse through its environment in a more intelligent way, learning to recognize and avoid obstacles or follow a given path based on the environmental stimulus presented. We use the information gained from the sensors, including object detection and subsequent transformation of images, in order to make a parking controller to park a robot in front of orange cones at a given distance, and subsequent expansion of the parking controller to a line following controller. The line follower is a natural progression from our previous wall follower, as it allows our robot to have controlled and planned movement outside of following the perimeter of a room. As taught in class, there are several different methods to implement pattern recognition. For this reason, before we began to implement the controllers, we had to decide what method for object detection would be best given our goals and constraints. The three methods explored were template matching, scale invariant feature transforms, or SIFT, and color segmentation. Gongi can now talk to us about the first method, template matching.
Thanks, Andrea. Template matching works by placing a template image on top of the input and choosing the offset and scale which matches the pixels most closely. Specifically, this gives us a bounding box that minimizes the mean squared error over each pixel. Next up, scale invariant feature transform, SIFT for short, works by finding characteristics in images which don't depend on perspective or scale. These are called key points. We decide which key points in the template match to key points in the input by analyzing local image gradients. This matching then lets us project where the template is on the input. Andy will now present color segmentation.
Thanks, Gongi. Color segmentation allows us to extract objects based on selecting for a certain hue. In order to do this, we need to utilize the hue saturation value, or HSV color space, because hue is what we're the most interested in. OpenCV allows us to generate a binary image mask where white pixels represent objects that are within a certain hue range and black pixels are on the outside, like such. We can then improve this mask before searching for an object by utilizing morphological operations. The closing operation will remove holes in the objects, and the opening operation removes small noise. We added an additional dilation in order to make the cone's shape more defined. We then use contour detection to find objects in the mask. We assume the largest contour would be the cone. We also make sure that it has an aspect ratio less than 1, or that it's taller than it is wide. Here's an example of the entire process. As you can see, it's more robust to occlusion or other possible orange objects, like in this example. We tested on 3 data sets. Sets locating a feature on a 2D map, locating a cone in a room, or locating the Citgo logo in different photographs. For cones, color segmentation is our best choice, and Gongi will explain why.
Thanks, Andy. Template matching struggles with changes in perspective and results in partial matches as seen in the top right. SIFT, on the other hand, is designed to tolerate these perspective changes, but is unable to find distinctive key points in the cone template. In the bottom right, we can see the resulting false positive, leading to a failed test. All in all, color segmentation gets around these issues since it doesn't care about shape. To measure performance, we used intersection over union, or IOU, as our metric. A higher value means the predicted bounding box is closer to the ground truth. Now, each algorithm excelled in one particular dataset, shown in green. As you can see, color segmentation is great for the cone dataset, but it doesn't work on the other two since it relies on the template having a single color. Template matching works best on the map dataset since it doesn't have to worry about perspective. Finally, SIFT works best on the Citgo dataset and doesn't work at all on the other two because they lack good key points for it to match. Now, once we know where the cone is in the camera image, we want to know where it is on the ground. Now, the problem is cameras naturally lose a dimension of depth, which is hard to recover. If we assume the object's on the ground, though, we can simplify everything to a 2D to 2D projection called a homography and avoid the lost dimension. The homography matrix requires 8 constants, which are specific to the camera lens and camera position. So we just need to calibrate it once. Using regular letter paper, we span the range of vision of the robot and took 16 pairs of points, shown in yellow, to calibrate the conversion between the image UV frame and the ground XY frame. And this conversion can now be used for all the pixels, not just the 16 calibration points. Kevin will now present the design of our controller.
Now that we have the location of the cone, we need to apply a pure pursuit controller so that the car parks in front of the cone. In a pure pursuit controller, a steering angle is chosen such that the vehicle would hit the reference point if the steering angle were kept constant. The lateral acceleration would simply be as shown. However, as our vehicle is a car and cannot accelerate laterally, we must account for the two-axle front drive nature of our robot, known as the bicycle model. Before I move on, I would like to point out that from geometry, R here can be written as L1/2 sine eta, which will be important in the next slide. This graphic is the representation of the car in the bicycle model. We applied Ackermann steering to the model, which results in a steering angle delta of arctan L/R. Upon plugging in our expression for R from the previous slide, we get a steering angle as shown, where L1 is the initial distance from the robot to the cone. To show the accuracy of the controller, the X error, Y error, and absolute distance were plotted, adjusting for desired parking distance. The car creeps closer in accordance with pure pursuit, and if the car realizes the distance error is greater than the tolerance, as seen in the box here, it will reverse and try again to reach minimal error. The controller also works in cases where the cone is behind the car. The car will turn at the maximum angle allowed by the hardware to get the front bumper to face the cone. If the turning radius of the car is too large to do so in one motion, the car will reverse and repark so that the error approaches zero. Nadia will now show the car in action.
Thanks, Kevin. We recorded a few videos of the car, as shown, to demonstrate its robustness even in a non-simulated environment that is not idealized. While it does well parking in front of the cone, we could not extend and test the line follower robustly due to time limitations. As you can see, we have multiple trials from various starting orientations and ending distances. From the test results above, the team has satisfied the objective of building and implementing a working real-world parking controller while allowing for future module buildups. Despite the success, there are still some key areas to work on. The color segmentation depends on specific lighting, since dimmer light can change the perception of the color and result in false positives. Moreover, there could have been a specific design process developed for turning the gains. By better optimizing the values to give a more precise controller, we can complete the task faster, since there would be no hesitation when backing up. This effective merge of perception decision-making algorithms allowed us to take one more step in the pursuit of an autonomous vehicle while maintaining a structured framework. Thank you for the attention. Are there any questions?